So we mentioned that water is amphoteric. It can act as an acid or a base. The process by which it does that is called autoionization. So what can happen is that you can accidentally advance the slide. Again, come on, I'm supposed to be able to put my hand down there. Okay. One water molecule gets together with another water molecule, and this was, well, I'm going to act as an acid, and this guy says I'm going to act as a base, and they do. And they pass off a hydrogen ion. How likely does that seem? How often do we see things become more different just naturally? We see things become more the same, right? Temperatures, the hot thing gets colder and the cold things gets hotter until everything's the same. Nature seems to be just trying to make everything the same. This doesn't happen very much. It happens a teeny tiny bit. Here we have water acting as an acid. It donates the hydrogen. It makes hydroxide. Here we have water acting as a base. It accepts the hydrogen, makes hydronium ion. And water does this with itself. Okay? So this one here, we're showing both of the water molecules. We're showing hydronium and hydroxide. This is the simpler version where we're using H plus instead of H3O plus. So we're only showing one water molecule, and it appears that the water molecule is basically falling apart. Now, is that what it's actually doing? No, because hydrogens are not out by themselves. This is aqueous, that means it is an H3O plus. This is an equilibrium, and we can write an equilibrium constant for that. It's called the ion product constant for water. So it's abbreviated KW. And KW is going to equal H plus times OH minus, or H3O plus times OH minus. Right? We don't have this in the denominator because it's a liquid. At room temperature, KW is equal to 1 times 10 to the minus 14. That's a good one to remember. It's not an acid ionization constant. It's the ion product constant for water. I don't care if you remember that it's called that. KW is good enough. 1 times 10 to the minus 14. So in pure water, the hydronium ion and hydroxide ion concentrations are going to be equal. Because every time you make one, you make the other. You can't have more of one or more of the other because they came from the same thing. You get one and one. So if the product constant, actually let's write this in. So KW equals H3O plus times OH minus. This is 10 to the minus 7th. If these are equal to each other, we could call them X, right? X times X. KW would be equal to X squared. And so these concentrations are equal to the square root of the equilibrium constant, which is 1 times 10 to the minus 7. That is a very small concentration, 0.000001 molar. Teeny tiny bit. But any water solution is going to have 1 times 10 to the minus 7th molar hydronium ions and 1 times 10 to the minus 7th molar hydroxide ions. So pure water is neutral. It's not acidic or basic because those concentrations are equal. What about this alkaline water that you could buy? Well, that means they've added something to it. Right? It can't be pure water. Any questions? So we can talk about acidic and basic solutions. An acidic solution is one that an acid has been added to. You add the acid, that creates extra H3O plus ions. A base solution has a base added that creates extra hydroxide ions. So what happens here, that was an equilibrium, right? H2O in equilibrium with H plus. and OH minus. So if we add an acid that creates more of these, what does that do to this equilibrium? We're adding product. It's going to shift towards the reactants, right? Because the equilibrium is like a really stubborn child, and you gave it some extra acid, and it's, I don't like that. And so it's going to do what it can to take it away. When it shifts to the left to decrease this acid content, it also decreases hydroxide ion concentration, right? And it shifts in a way that the ion product still applies. So after it's shifted, H plus times OH minus still equals 1 times 10 to the minus 14. But now one is bigger than the other, they're not equal. In the basic solution, we've got extra hydroxide ions. More hydroxide ions also causes it to shift, causes a lowering in the hydrogen ion concentration. So acidic solution, the hydrogen ion or hydronium ion concentration is higher than hydroxide, and in a basic solution, it's the opposite. Here we have H3O plus concentrations of 3 different solutions. Which solution is acidic? So what are we looking for? What are we looking for? Pure water, it would be 10 to the minus 7, right? An acidic solution, the concentration needs to be bigger than 10 to the minus 7. And so that's this one, 10 to the minus 3. 10 to the minus 9 is smaller. So that one's acidic. What is C? That one's going to be basic. And how about B? It's going to be neutral. So we can use KW in calculations. If we know what the hydroxide ion concentration is, we can calculate the hydronium ion concentration. So the short version of the equation is like this, and KW is going to equal H plus times OH minus, and that equals 1.0 times 10 to the minus 14. So if we have a hydroxide ion concentration, and we want the hydrogen ion concentration, we can rearrange this. So we divide both sides by the hydroxide ion concentration. These guys cancel out. So, to calculate this guy, the hydrogen ion concentration, which is exactly the same as the hydronium ion concentration, we've got KW divided by the hydroxide ion concentration. Now, do it on your calculator to make sure that your calculator is cooperating. Because yesterday we had some calculators that needed to be spoken to. The problem with calculators that happens is if you're not using the scientific notation button, the EE, if you're doing 1.0 times the anti-log button, 10 to the, and you're putting minus 14 in here. And then if you divide by 1.5 and you hit multiply, it takes this first part and divides by 1.5, takes that result, and now multiplies it by 10 to the minus 2, which is not what you wanted to do. You really, if you haven't yet, you really need to learn how to use the scientific notation button. It makes life much easier. Otherwise, you could put parentheses down here or use that box over box fraction button. Anybody need me to talk to their calculator? this one? The hydroxide ion concentration is 10 to the minus 7. Do we actually need to calculate it, the hydronium? Isn't that the concentration at impure water? Yeah? 10 to the minus 7? Because in pure water, the hydrogen ion concentration and the hydroxide ion concentration are equal to each other. I would not necessarily expect you to just pull that one out, especially today. But this is the square root of KW. So then this one has to be the same. You can set it up like this and solve it. Nothing wrong with that. You'll get the same answer. Okay, how about this one down here? Again, KW over the hydroxide ion concentration. .2 times 10 to the negative 5. There's one more thing. It's asking us, are these solutions acidic, basic, or neutral? So let's look at A. I find it easier, more straightforward to look at the hydrogen ion concentration. If the hydrogen ion concentration is greater than 10 to the minus 7, it's acidic. Is it greater here? No, it's less. So this must be basic. You can also look at this one and see that this is bigger than 10 to the minus 7, so it's basic. What about the one in the middle? Neutral, because they are equal. And the one on the bottom? Acidic. So of course they're going to do one of each. Any questions? Yeah. Okay, this is where we're at. So the concentrations of hydronium ion are all over the place. They could be as low as like 10 to the minus 14, or as high as like 0.1 or 1 molar. So 14 orders of magnitude. It's a huge spread. So we use the pH scale to make that more compact. The pH scale, the pH, we're looking at powers of 10. So now instead of 14 orders of magnitude, we're looking at 14. So this is the definition of pH. pH is the negative logarithm of the hydronium ion concentration. This is the negative sign and the base 10 log. It's not anti-log. So if we have a solution where the hydronium ion concentration is 5.3 times 10 to the minus 8 molar, then the pH would be, we have to calculate it. The negative log of that number. On the 36X Pro, to get the base 10 log, you have to push the button twice. You push it first, it says ln. You push it again, it says log. It's a little annoying until you get used to it, but then you're okay. And there's a bunch of digits after that. I would round this to 7.28. Are the calculators cooperating? Any questions? Sig figs. So this had 2 sig figs. This looks like it has 3, right? But we got a little note down here. In a logarithm, only the numbers to the right of the decimal point are significant figures. I'm not going to try to trick you or beat you over the head with that, but I do want to explain it to you. This 0.2757 that we rounded to 0.28, this part comes from the 5.3. The 7 is related to the 8. So the negative log of 5.3 times 10 to the minus 2 is going to be 1.28. Test me, check me. Did I do it right? I did. Negative log of 5.3 times 10 to the minus 11, 10.28. As if we think about something that's a little simpler, 1.0 times 10 to the minus 4. When you take the logarithm of that, it's saying, what power of 10 is this number? Well, the log of that would just be that exponent negative 4. And we don't want to have negative numbers, so we put a negative over here, and that makes that positive. Negative log of 10 to the minus 12 is just 12. So the digits before the decimal point are essentially the placeholders, right? That's just telling us where does the decimal point belong, right, in the original number. The digits after come from this part of the number, and that's where the sig figs are. So 2 sig figs here, 2 decimal places in the pH. And what I really want you to know is, if you're not sure about how many to put a couple extra. You can always cut them off later. If you put too few and round it too much, you have to do the problem over again, and nobody likes that, right? And so, we might be tempted to round this to 7.3 because it looks like it has 2 sig figs, but we're throwing away information. Any questions? That's what I was just trying to explain. All the numbers to the right would be the significant figures when you take the logarithm of something. So I accidentally erased what I had written here. Oh, I got the number in my calculator. 7.2757241.3. That's what my calculator's showing me. And I want to round it to 2 significant figures because that's what my concentration has. These guys are the 2 sig figs. So we're going to report that as 2.8. Because this part, the 7, is related to the 10 to the minus 8. So the way I did that trick, 5.3 times 10 to the whatever. If it's negative, whatever that number is, minus 1, 0.28. You can do all of them. Yeah. Did that help? A little bit? Any other questions? So here's the pH scale. It runs from pretty much 0 to 14. So here we have a nice range of numbers instead of 0 to 10 to the minus 14, right? So small pH means it's acidic, and large pH means it's basic. I know that seems a little backwards. pH less than 7 is acidic, neutral is 7, pH greater than 7 is basic. We can also look at a pOH value. The P is just a function, negative log of. whatever's after it. And so that one's going to be sort of a mirror image of the pH scale. And then this is interesting. Concentrated acid solutions can have negative pH values. What? So if we had a pen that we could write with, if we had something that was 18 molar, there is an acid that the concentrated form is 18 molar. So that would mean, if it's a strong acid, that would mean that the hydrogen ion concentration is 18 moles per liter. That is really, really big. Negative log of 18. Negative 1.26. Two sig figs here. Oops. Come on. I want you. Two sig figs here, 2 decimal places there. Any questions? So calculate the pH of each solution, indicate whether it's acidic or basic. So we're given the hydronium ion concentration. pH is the negative log of the hydronium ion concentration. So the negative log of 9.5 times 10 to the minus 9. This is going to be 8 point something. I forgot to do negative log. 9.5 times 7 minus 9. 8.02. There's more digits. I'm just rounding it to 2 sig figs. Is that acidic or basic? It's basic. The pH is above 7. That's basic. So this is a basic solution. You could look at the hydronium ion concentration and see that that's smaller than 10 to the minus 7 and do it that way. Okay, here we're given the hydroxide ion concentration. But the pH equation needs the hydronium ion concentration. So we have to calculate that first. And that's going to be equal to Kw over the hydroxide ion concentration. Kw is 1 times 10 to the minus 14. And divide by hydroxide. We did this a couple of slides ago. .4. There's our 2 sig figs. I'm going to add 2 extra digits because I'm not done with this number. 0.8 times 10 to the minus 12. So then pH is the negative log of 1.408 times 10 to the minus 12. Um, 11.85. I'm done swimming around it. Acidic or basic? Basic. Greater than 7. Any questions? what if we're given the pH and we want to find out the concentration of hydronium ion? Well, we need to rearrange an equation then. pH equals negative log of hydronium ion concentration. I'm going to show you how this works, but then you can just memorize the rearrangement. So I'm going to multiply both sides by -1, so this becomes positive and that's negative. And then to undo a base 10 logarithm, we do 10 to the x. So 10 raised to this side is equal to 10 raised to that side. Log and anti-log, poof, go away. Like matter and antimatter, they cancel each other out. So the hydronium ion concentration is equal to 10 raised to the power of the negative pH. So in this example, the hydronium ion concentration is 10 to the minus 8.37. That's not a good answer though, right? Because we could have it in scientific notation, but then the exponents have to be whole numbers. So we have to calculate this. And so you're going to use the anti-log button, which on my calculator has e to the little box or 10 to the little box. I press it once, I get the natural one. I press it a second time, I get 10 to the, and I do negative 8.37. And that's what your calculator might show you. Why did it stop? Because it can only display 10 digits. Are there more digits after that? Yeah, there are. So I don't think I intentionally trick you. I did in Chem 1A. I don't think I intentionally trick you with this on an exam. But you get a number like that, and you're like, that can't be just 4. That'd be too simple, right? We need to find out what the rest of those numbers are. So you can tell your calculator to show you this number in scientific notation. And the way you do that on this 36X Pro is you hit the mode button, and then you go down to the second line where it's norm, psi, eng. And you want scientific notation. You highlight that and press enter. And then you quit to get out of there, and then you're like, oh no, my number's gone. Press enter again. Oh, there it is. Now it's showing you 4.265. That's a 5. So yeah, there's lots more digits in there. How many do we want to keep total? This is a pH. So in a pH, only the digits after the decimal point. So we call this 4.3 times 10 minus 9. Now, if you wrote 4.27, would that be wrong? No. Close enough. Any questions? So we've got a pH scale. We can also have a pOH scale. And this refers to the concentration of hydroxide ions. So pOH is the negative log of the hydroxide ion concentration. So that P, as I mentioned earlier, stands for negative log of. pKa, we saw pKa's in that table of acids. That's the negative log of the acid ionization constant. It takes numbers like, 5.3 times 10 to the minus 9 and turns them into 8.28, which are much more compact, easier to remember, easier to work with. You could have P of anything. It's the negative log of that concentration. Derive the relationship between pH and pOH. I'm not going to make you do this. I'm just going to show it to you. Kw is equal to the hydrogen ion concentration times the hydroxide ion concentration, right? I'm going to take the log of both sides. I'm actually going to take the negative log of both sides. Why do you want to do that? Well, because of what's coming later. When you take the logarithm of two things that are multiplied, it's the same as the logarithm of each of them added together. So the log of xy, x times y, is the log of x plus the log of y. And that's actually why logarithms were first used, created, thought of, whatever. Because before calculators, before long multiplication, how did you multiply big numbers? You took the logarithm of the two numbers you wanted to multiply, you added them together, and then you did the antilog. Well, how did you do the log and the antilog? On a slide rule. That's what slide rules were for. Personally, I don't know how to use a slide rule. But I have one that's 7 feet long, hanging on my wall in my kitchen. It was a lecture demo one, right, for a classroom. They had 2 of them, and they just threw them in the garbage. And my husband's like, those are too cool. So they brought them home, we hung it on the wall. That allows you to go back and forth, log and inverse log of numbers. Like I said, I don't know how to do it, but you can do it. So anyway, that means that this is equal to negative log of H plus the negative log of OH minus. Right? And how do we abbreviate negative log of? P. pKw is equal to pH plus pOH. Kw is 1.0, bless you, times 10 to the minus 14. The negative log of that is 14. pH plus pOH equals 14. And that comes directly from this. But if you've got pHs, it's the number between 0 and 14, and you just add them together to get 14, it's really easy. If you're doing it this way, you've got some number times 10 to the negative something, and then you're trying to find this other one, and you have to take 1 times 10 to the minus 14 and divide it by this other thing, and it's just kind of long and messy. So I really like this one. Any questions? And now we get to the circle of life. No, the circle of pH. So we've got all these equations and these numbers, and they're all related to each other. We've got pH, we've got H plus, we've got OH minus, and we've got pOH. So you can convert between pH and H plus. You can convert between H plus concentration and OH minus concentration. move that over, because yesterday it was more of an oval, and the oval of pH just doesn't have the same ring. It used to be a circle. And yes, that is my own stupid joke that I came up with. This is the circle of pH. So, if we're trying to find the pH and we're given the hydroxide ion concentration, we just did a problem like that. Could we come up with an equation that links these directly? Yeah, we could, but it's not worth doing. You convert this to that and that to this. Or you go this way, hydroxide ion concentration to POH and then to pH. So any two things here, you can convert one into the other. Which way you go around the circle just depends on your own preference. Up here's the one we just derived. pH plus POH equals 14. Any questions? So as the pH of a solution increases, meaning getting bigger, a larger number, what happens to the acidity of the solution? It decreases. It's going to go down. And those sorts of questions can be a little confusing, and you kind of have to step back and say, okay, what am I really thinking about here?